So today we have a great pleasure to welcome Mark Herbster, who is part of the CSML and AI centers at UCL. He's also a director for the MSc in Machine Learning in UCL, and his work focused mainly on online learning. And today he's going to talk about online multitask learning with long-term memory. And if you have any questions, feel free to interrupt him. You can unmute yourself, or otherwise you can post them in the chat.
Okay, hi everybody. Thank you for the welcome. It's my pleasure to be here. Thanks for the organizing these seminars, Antonin, and the other organizers behind the scenes. This work that I'm going to discuss today is work with my PDRA, Stephen, and my work, Lisa, and it builds on a lot of work done with other collaborators in the past. As Antonin said, this is meant to be fairly casual. It's a relatively small group. So really, if there's something you don't understand or you like more clarity on, or you just have some thoughts, do feel free to interrupt either via chat or just turning on your camera or not turning on your camera and saying something, and we'll interact. Okay, so this is online multitask learning with long-term memory. So I know in the days of COVID, we think of online and, a lot of teaching online. Here, I'm talking about the online learning model. So in the online learning model that I'm thinking about, as opposed to perhaps the normal batch learning model, you receive a data point, you make a prediction about its label, then you receive another data point, and you make a prediction about its label, and and on each trial you do then receive the true label of that data point, and you incur some loss. And that's essentially the setup of the model of online learning that I'm working in. Interesting thing about this setup is that well, we're going to be able to prove bounds that we can do without probabilistic assumptions. Okay. And we'll get into the model and explain how that's possible in a moment. Okay. Yeah. So one thing that our online model, well, maybe we'll see with the model in a little bit, but essentially the way we're going to be able to work without predictions is we're going to try to do relative to some comparison class or hypothesis class of other predictors. So we consider that our algorithm does well if we do well relative to any given hypothesis in that class. That's the normal online learning model. But now, to make things kind of even more adaptive, we're going to allow that underlying predictor to change. So, for instance, perhaps first there's some linear predictor which is good on your data sequence for a while. It predicts relatively well with, small loss. And then there's maybe another predictor in the future that starts to predict well, i.e. something about the data is changing over time. For instance, on a MSc project this summer, worked with a company that does all sorts of buying and trading on the US energy market. So there's a bunch of different power companies where they each have their grids, and they're constantly setting prices and buying energy every day from different producers, and it's a way to kind of make the market efficient for energy. But they're trying to predict well what are good buying strategies, but these change very much over time, which kind of brings us to the second thing. So not only do we want an online system that's going to be adaptive to a changing thing, we're interested in, maybe this is too strong a language, eternal return. But the idea is that somehow in our adaptive model, first maybe one predictor is good and then another predictor is good, but what's going to be really important and what kind of makes the problem challenging is that there's going to be some element of memory to our system, i.e. we want to pay less if something that was once good in the past becomes good again, i.e. And, if we believe these ideas, eternal return, things in the past we're likely to perhaps see again as good strategies for us. Okay, so continuing, right, so we're going to get to the formal model in a moment. Don't worry, for those of you who like equations, there's going to start to be too many of them. But the basic idea is we're going to have some hypothesis class, and these hypotheses will be functions that fit the data. This could be all sorts of things. These could be polynomials, they could be linear predictors, they could be arbitrary algorithms that have been trained on some data set. And so we have some set of these, potentially an infinite set. So the normal online model, in its simplest form, we want to compete against a single hypothesis. We want an algorithm that does well. So the underlying thing is that, we want to do as well as a single hypothesis. And so here, in this talk, I'll tend to interchangeably use hypothesis, color, and mode to all mean the same thing. The color is kind of very graphical. You can see what I mean by changing, and mode, we use this language in the paper. So another version of the online model is maybe first one linear predictor is good in the data, but imagine it's power demand, and in night the power demand is different than the power demand in the day. Then there's seasonal, and there's all sorts of things. So it could be that your predictors are changing over time, but not quite in a structured, predictable way. And things that were good in the past might be good again. Now, it's relatively straightforward to give an algorithm with good theoretical guarantees if we don't account for things that were good in the past being good again in our bound. Once we start having repeated modes or hypotheses, things become hard, okay? And then to make the problem further more interesting, we're not going to just have one time stream, we're going to have multiple time streams. We'll get to this model in a moment, where even though I'm calling these tasks, you can imagine that these are, for instance, different agents. Maybe these are our drones flying through the sky, each facing its own prediction task. Maybe this is power demand in task one in one part in the US, then this is power demand in the US in some other part where you're trying to predict. And the idea is that we want guarantees that can exploit, if task one sees this at this time period, we're hoping in task two, when we see this, that it can exploit the fact that task one has already seen something that was good there. And likewise, when we see this screen here, we're hoping that this can somehow be exploited by the system, okay? So, in the back of my head, I have a bunch of agents, and they're all adapting, and somehow they're cooperating and they're sharing information. This is kind of the picture in my head. Okay. Give me a moment. Okay. So outline of the task today. So we'll review what we mean by online learning, the single task and a single mode. We'll then introduce switching, and to kind of give us an idea of what we'd be aiming for an efficient algorithm. We'll show some algorithms which require exponential time, but our goal will be to do things efficiently. The research that this talk is on has really kind of two distinct things. They're in the same model. We have finite hypotheses classes, and we have this kind of potentially infinite hypothesis class consisting of functions formed by linear combinations of kernel functions. Today, we're only going to really focus on this, though we will mention those results. Yeah, then, paper's fairly technical, but, we're going to try to give you some guide to how we solve this problem, the RKHS setting. And in fact, the way we're going to solve this problem is we're going to reduce it to a very sparse matrix completion problem, where the matrix completion problem is going to be so sparse that, a common case would be that we would just be predicting the diagonal of this matrix completion problem, okay? And so this is where we're going to get to. But first, let's set the stage, review finite hypotheses, classes, and bounds. Then we'll give us an idea of some, what's a reasonable bound to get. And yeah, let's take it from there. Okay, classic results. So what is our online learning model? Our online learning model is the following. Learning takes place over time. And on each time, we receive some pattern from some input space X. And our algorithm needs to make some prediction or take some action, and that's in our prediction space, our action space Y. So it predicts YT. Then we receive the label or the name of the best action, and we're hoping that YT and YT hat match, and we pay some loss for the amount that they mismatch. And so our goal will be to minimize the total loss in this sequential setup. Okay, so where this is just the total loss, it's just the sum that our algorithm experiences over all the trials. So our goal is going to be to design algorithms where such that the total loss is small. So the question is, how can we do this without distributional assumptions? How is this possible? Well, it's what we were hinting at before, and now we just add some mathematical notation. So no distributional requirements. The data is not assumed to be generated probabilistically. It could be generated adversarially, could be generated in some helpful manner. We just don't know how. The model doesn't make an assumption. So we're not going to give an absolute bound, because that's kind of impossible, because in this probabilistic free model, if there's some adversary generating the data, it could always just choose the worst thing with respect to what we predicted. So it forces us to make maximum loss each trial. So we have to do something. So what we do is we give a relative bound relative to some set of predictors. So we know the loss of the algorithm is just H, but then we can speak, is just this LA, but then we can speak of the loss of any hypothesis in our hypothesis class of predictors, and that will be, so the algorithm predicting, it'll be just the hypothesis that we're, from this set of predictors that we're comparing against. So typical things is maybe we want an algorithm that does well against all degree 2 polynomials, for example, or all linear classifiers and so forth. Our aim is to prove some regret bound. So this is what we mean relativized. We want our algorithm to do not much worse than the loss of any hypothesis in the set plus some small amount, okay? So this is the type of bound that we hope to do. So if we prove this with respect to any hypothesis set in the thing, well, hopefully it'll be small. It'll then be small relative to the hypothesis in the set that has a small amount of error. Okay, and so today we're going to be working with two hypothesis classes, quite kind of classical. One is we just have, some finite set of functions that map X into binary things everything today is going to be binary prediction. Okay, so we have just some set of arbitrary functions that map x into -1 or 1. So we just have a finite hypothesis class. Otherwise, we're going to have a hypothesis class based on reproducing kernel Hilbert spaces, i.e. just some linear combination of kernel functions. So for example, in the back of your head, maybe you have the set of all linear combinations of Gaussians, general linear combinations, and you can imagine adding your Gaussians together to kind of get a very large class of smooth functions. Okay, so historically, bounds have been proven for this setup. Okay, so in the finite hypothesis setting, I never quite know who to give credit to, but I'll say hedged weighted majority in the aggregating algorithm came up with the following result. And for today, the results are much more general, but to keep things simple, everything is going to be for the 0-1 loss, i.e. we predict one of two labels and we either get it right or wrong. If we get it right, we pay 0. If we get it wrong, we make a mistake and we pay 1. Okay, so kind of a classic result there. If you give me a finite hypothesis class, there exists an algorithm whose regret is bounded by 2 log n over t. Okay, yeah, some of you may be going, Herbster, you said there's no randomness on the data. What is this expectation here? Our algorithm, which achieves this bound, has some internal randomization. And so this is relative to the internal randomization of our algorithm. And the nice thing that people commonly observe about this bound is 2 things. One is the bound grows pretty slowly in the size of this finite hypothesis set. It only grows logarithmically. So this set of finite hypotheses can be really, really large. We're not going to pay much in our bound. Okay. And likewise, yeah, I mean, the issue with having very large sets is actually, having to collect the predictions of a large number of things. So even though we can have a large set of things and we have a small bound, it might have time costs if we were to run such a thing. And then, we also regret scales with the square root of t. So observation is, if we kind of let our bound go to infinity, that our algorithm won't do much worse than the best predictor in the set asymptotically. Okay. Then kind of putting results together, another classic thing for kernel predictors, if we have a kernel and we have some data sequence with something that looks like online gradient descent, we can get the same sort of bound for any hypothesis in an RKHS, where this is the norm of the function in the RKHS. This is kind of the maximum norm of any of the instances in the RKHS. And the slight difference between this bound and that bound is now this term, all predictors in HN are treated equally. We pay the same amount for each predictor. Whereas here, the more complex the function, the higher the norm is. In some sense, functions which are less smooth tend to have higher norms. We will pay more. Okay. And this is a little bit of odd notation. I just want to be clear what I mean here. What we mean is any function in the RKHS which interpolates on the data points, i.e. we're not considering taking a function from the RKHS and making a linear classifier out of it. We're using the function directly. So the function has to interpolate on the data points that we see. Both of these bounds, which I've given you, depend upon knowing some single tuning parameter. there's generalization of these algorithms where the bounds don't really change except by constant factors pretty much that get rid of these parameters. But in general, all bounds we present today depend on kind of choosing the right tuning parameters. I explained this, but essentially pointing out that we're, in the RKH case, we're going to be talking about things that interpolate. So there's a difference between linear classification and interpolation. Some of you may go, well, Herbster, why don't you just do linear classification with kernel functions? That would be better. I do want to point out that there's no known efficient algorithms that achieve regret bounds either in Rn or in the linear classification case. I don't think there's a proof that such a thing can't exist, but there are no known efficient algorithms there for a hard open problem. Okay, I'm not going to go over the algorithms that achieve these, but this is kind of the classic exponentials weights algorithm expert case. And then this is basically online gradient descent relative to a variant of the hinge loss, then kernelized. So these algorithms achieve those bounds, and we there's randomization in both of these algorithms. Okay, so that's kind of quite old history. Then people are interested in where we do switching. Let's just, where switching is, maybe first one function is good on the data, then maybe the red function is good on the data. But the point is, when we get some data sequence, we won't know these boundaries, nor will we know the colors, hypotheses, or modes. Okay. Okay. Okay, so we're going to hope to prove bounds that depend upon the kind of complexity of this sequence. So a simple way of parameters that help us measure the complexity of the sequence is the number of switches, which we'll denote by K, and the number of modes, which we'll denote by M. So where H star is just, our switching models, first we had a single hypothesis, but H star will be, what if we had a sequence of hypotheses, a different one for every trial, okay? So we two properties of this sequence is the number of switches. So this is a switch, this is a switch, this is a switch. So there's 5 such switches, but there's only 1, 2, 3, that's the same color, 4 colors, okay? Modes, switches. Our algorithm won't know these. Yes, and now we want to compare against any sort of H star, where an H star is, the loss of that is just the loss of the constituent sequence of hypotheses. Okay. How can we get an inefficient algorithm to achieve this? Well, basically, we're going to grab the set of all such. So in the H star set, we'll grab the set of all such H stars. So for instance, here's some given H star where the first 3 trials are all colored with the same hypothesis, 4th trial is colored with the second one, then we return to the first, and so forth. We're going to take, and we're going to call this is some particular meta hypothesis, okay? And so then what we can do is we can take the set of all such of these meta hypotheses. Here's a sequence of hypotheses. And then we grab all of them with K switches with no more than M distinct colors. So a meta hypothesis colors each trial in T with the hypothesis from HN. Jumping down to 4 here, recall we had this bound which only growed logarithmically. So one way of creating an algorithm to solve this problem is take our original hypothesis set, create this meta hypothesis set, and then we just plug it in to get our bound. And so, rough combinatorics to bound this gives us, if our set, we have n base hypotheses, we're only going to color our sequence with m colors, so we need to choose m colors out of n. So we have that term in our hypotheses. We have to choose the trials where when a given color sequence starts. So this is roughly t minus 1 points. We have to choose k colors. And then each of those segments that we're going to color, there's something like m to the k plus 1 of them. And if we take the log of that, that's not such a big number. Problem is look, we get a reasonable bound. We'll discuss this in a moment, but the algorithms are inefficient. This problem was solved. This is posed as an open problem by Freund, was solved by Bousquet and Warmuth, and then improved on by Coulomb, Damsky, and Warmuth 12. Damsky, who's also teaching, who's the program director for CSML. Okay, let's continue. Okay, so this gives us something to aim for in the finite hypothesis case. We'll get to the multiple tasks later, but now let's consider the kernel case, okay? Now, this previous argument doesn't work so directly because HK is going to typically be infinite. You know, you're going to have an infinite number of linear combinations of Gaussians. Okay, so, but we're going to do the same kind of argument before. We're going to use this hedge-like algorithm as a controller, but then it'll be running tons and tons of kind of meta things, where the meta things aren't hypotheses because the base hypothesis set is infinite. It'll be meta learners. Okay, so a given meta learner is going to consist of some m instances of this online gradient descent trial. The color of the trial is associated with the online gradient descent instance. So, you know, an online gradient instance only runs on its colored trial. So for instance, here we start running one online gradient descent instance. This is our meta learner H. We stop running that instance, start a new instance of online gradient descent, swap out, restart that first one, and continue. So we can consider running all such online gradient colorings of things with online gradient descent learners. Okay, and then once more, to get an idea what a reasonable bound to search for, the loss of this meta learner consisting of learners is the sum of the losses of each of the m meta learners, i.e., you know, we get the loss of the blue one, the loss of the red one, the loss of the orange one, and so forth. So the way I described before, each one is kind of receiving its own online partition of the data sequence. So there's no crosstalk between the learners. And so once more, to bound the loss of a particular meta learner, it's just the same bound we had before, but summed over the m meta learners and their own time lengths. Then we take all the meta learners and we mix it with this hedge weighted majority aggregating algorithm and doing a few inequalities. We plug it in and we get this as a bound to aim for. Okay. So what are some considerations? Considerations are the following. I kind of want to point out, so this is the finite hypothesis case, which we've got in a target. This is the reproducing kernel case, for which we've got in a target to aim for. What is the difference between these two setups, or what do we have in common? So these terms are the same, and then these terms are different. These terms are kind of where we're specifying the position. So we need m meta learners, and we're saying which each of the k segments are colored with, and then this is saying where these segments start. And so there's k such segments, and each segment is of length roughly t over k, so it takes roughly k log t over k bits to express them. So this is the common term, and then it's kind of natural to think of these terms as the price that we pay for learning the meta learners, i.e., this is learning what are which of the m hypotheses that are good from the set of n hypotheses, and this is the price for learning the m learners. Okay, so I think of those as learning complexities. Our goal is to obtain these with efficient algorithms. Any questions so far?
I do have a quick question, Mark.
Yes.
So at any given time step, there is only one learner that is active. Is that the case? Or like in
this exponential simulation, that is the case. We haven't said how we're going to solve things, but
right.
Okay.
Right. So just to clarify, like, I mean, just to get the clear picture about this, the switching is something related to the learner, right? Like the learning mode or whatever the learning model that the learner uses. The switching is not happening in the competitor class.
The switching is not happening in the competitor class. We have a base set of competitor classes. We have a base competitor class, and then the idea is that we want to take that competitor class and get a switching competitor class by allowing a different competitor for every trial.
Okay.
Okay. We'll come back again. Okay, so now we're going to start to get into new results. We kind of know what we want to aim for bounds. So the way we're going to make things more complicated is now you imagine that we don't have a single time stream for which we see things again. We have a series of tasks or a series of agents which each have their own private time streams, and we hope to do well when things are repeated across time streams, and we hope to have efficient algorithms. This is the model. This is essentially the same notation as before. Rather than going through the notation, I'll just go back to the slide to point out the way the notation works is adversarially, we don't know the process. Somebody says, oh, task S or agent I needs to make a prediction. So then it makes its first prediction. Then maybe something says, okay, task 3 needs to make a prediction. Then it says that task 3 to make another prediction, and so forth. Then maybe we go back to this, and then maybe we go there. So the way we get data for the different tasks, we could get it in a friendly way. Maybe we get one for each task at a time, or maybe we go through the task sequentially. But the point is, we don't care the order in which we get the data, as long as it's sequential within task. Okay, so that's the model. So it's the same model as before. We get the task, which is active. We have the local time for each task, and our goal is to, just minimize the total loss again. Okay, so everything kind of follows through in this generalized model. Switches, we're just counting the number of these breakpoints. Modes, we're just counting the number of different hypotheses. So definitions are just the direct extension. Doing the combinatorics, I did the combinatorics in the single time thing because essentially combinatorically we could have made the same arguments where the switches reduced to, or combinatorically the tasks can reduce to switches. Algorithmically, even if we had an algorithm with memory in the single task case, there's not a way to reduce that to an algorithm which works in this model. Okay, continuing. Okay, yes. So this is what we're not going to talk much about today. this is based on we did this in the finite hypothesis class case. We have an algorithm for this. It's very directly based on extensions to methods used in K-12. We're not going to include it. My basic comments about the algorithm is we do pretty much match the bounds up to constant factors. So it's really, we get a good bound for this setting. Algorithm is linear time in the number of things in our hypothesis class. And if we have S tasks, it's going to require something like OSN time complexity. And we've implemented it on synthetic data. It works cleanly and it's pretty straightforward. Not going to go over the algorithm. I mentioned the things here. Too much thing. We're really going to be interested in the reproducing kernel case. We also have a result there. We can't kind of match the exponential time algorithm in terms of bounds. So I'll explain that difference in a moment. And our algorithm, the point of it is it's not exponential time, but it is going to be an expensive algorithm. Okay. Well, just summarizing what I said and putting the bounds up. So in the single task case for finite hypotheses, we get a bound that matched the exponential argument up to the constant factors. For HK, our exponential time algorithm, we got a bound like this for exponential time. For our at least, in practice, T-cube time per trial is pretty expensive. But our polynomial time algorithm, we don't quite match. Where the major difference is, at least with the most impact, in my opinion, is that this log m becomes an m, so we pay linearly in the number of colors or hypotheses in this term. And then, our log, we introduce an additional log t factors and log t's, which aren't so bad. So this is kind of the major way in which what we lose, and it's going to be pretty much an open problem if there's an algorithm that can achieve this efficiently. But I do want to point out, it's still a pretty good bound in the sense that, the fact that we can, our dominant term in many cases is still going to be these learning complexity terms. So this term isn't too big a term normally. K and M could obviously, there are cases where it could be too large, but we still somehow only managed to pay once for M different things in our RKHS, which is, in my opinion, good. Okay, so that's kind of what we're going to achieve. Now I want to do what little bit I can to tell you about how we do this. This is kind of technical, but the idea is we're going to take this online learning multitask problem, and we're going to, in fact, reduce it to a very sparse inductive matrix completion problem with side information. When you see the matrix that we get, it can be crazily sparse. We might just have observations along the diagonal in the common case. It could be that it's not just along the diagonal, but we're still going to get non-trivial bounds for online matrix completion with a matrix that this is where we see the data. Okay, so since I'm going to reduce this to inductive matrix completion, let me kind of introduce this tool of inductive matrix completion, which we give results for. Okay, so the idea of inductive matrix completion is now, our matrix is indexed by some set I and some set J, where these correspond to the spaces associated with the kernel. So imagine for instance, we have our matrix, and so maybe this is a Gaussian kernel on RD, and maybe this is a Gaussian kernel on RD prime. And so here, our index set, rather than just being like, you normally have an m by n matrix, our index set could, these would be vectors in RD in that dimension, vectors, RD prime, vectors in RD in that direction. Okay. So we have potentially a very large inputs space. This is kind of why we call it inductive. So we get indices from our matrix that we want to predict, and it's just the usual online game. We predict a label, we receive whether it's true or false, we incur loss. Okay, so we say we have side information because we have kernels on the rows and kernels on the columns. We'll come back to what we mean by that in a moment. Our aim is, we want to prove regret bounds, where the regret bound depends upon the matrix that fits the data that we see, the two kernels and time. Okay, so for instance, with Gaussians, I and j might potentially be infinite. So speaking more generally, one thinks about matrix completion. People like to think about the classic Netflix problem. We have users and we have movies, and we have some ratings for some users and we have some rating for movies. What is the inductive model saying? Well, one way to think about it is that we have a feature vector associated with each user, maybe their age, maybe where they live, I don't know what features, are these days. I guess we probably have lots of demographic data on everybody. And likewise, you have some feature vector associated with movies. Maybe it's a category, maybe it's action, romance, drama. Maybe we know some of the actors that are in it. And so, in the normal matrix completion model, let's say you did matrix completion, you get a new user without any information about that user. There's no way to kind of get a new prediction for that user. But the kernel function, i.e. the fact that we have kind of feature vectors for each user and movie, allows us to extend to this case in some way. When we get data about a new movie or a new user based on its features. And so at a high level, the feature vectors, the expectation is if two users share the same features, that they will tend to like the same movies. Two movies which share the same features tend to will be liked by the same user. All this done softly. That's the idea of online inductive matrix completion. Okay. You saw when we did online gradient descent, we got a bound for doing as well as the best function in some kernel space. So for instance, could be the norm in that kernel space. To be able to talk about bounds for inductive matrix completion, I need to shorten this talk further. But we're going to need some sort of complexity measures for our matrices. Okay. And so in this work, we use one complexity measure for our matrix, the max norm, where this is kind of well known. It's not as commonly used as the trace norm, but it makes some sense. What's more, it's one of these matrix factorization norms. And so we have some factorization of the matrix by some matrix P and MD, some matrix Q and ND. And I don't think I have time to really go over too much on the properties of the max norm right now. This is going to be one term that we're going to use. Another term, which we don't know much about, but of course I'm interested in any insights you have here. The other kind of term that we introduce, which is going to depend upon our side information, is something that we'll call the quasi-dimension, which we're going to discuss further. But these, once more, depend upon a factorization of the matrix U. and they now depend upon the kernels M and N. Okay, I'm leaving out a lot of notational details and technicalities here. Okay, so we went ahead and improved the bound for this setup, where it depended upon these two terms. It depends upon the quasi-dimension and the max norm. For those of you who are familiar with Novikov bounds and margin, this max norm really bears a lot of parallels to what you can think of as the margin in SVM, but I won't go into the details here. We think of D as quasi-dimension, yes. And so if we've seen data that ends up in an M by M matrix, we got this bound, but these are our kind of dominant data dependent terms, and we'll focus on them. This is, based on a great deal of research that got us to this point finally. First bounds for matrix completion without site information was given this paper. We have references at the back. I'm not going to try to explain the algorithm to you right now, but it takes cubic time per trial. And because it's inductive, it's kind of expensive. Okay, so when we went back, our bounds depend upon this product in the algorithm. We don't need to know these terms exactly. We just need to know upper estimates. And so I wanted to try to give you an idea of how these, okay, I'm going to aim to end at right at 5, if that's okay.
Yeah, that's fine.
And
you can take a few.
And then anybody who wants to see questions, stick around. What?
If people need to leave, they can leave, and then we'll post it on YouTube anyway, so people can watch it later.
I
won't. Can go a few minutes.
I encourage you to leave when you're ready to leave. Okay, so the point is we kind of want to we want to understand our bound in terms of interpretable properties of view and side kernels, and kind of the key interpretable property is going to be this concept of latent block structure and bi-clustering. And we're going to give you 3 perspectives on latent block structure and what we mean by latent block structure and bi-clustering. Starting with perspective 1. We say a matrix is KL bi-clustered after a permutation of the rows and columns. So i.e., here's our given matrix. And if there's some way of permuting, we choose some permutation of the rows and columns. If there exists some permutation such that it can be organized into K by L rectangular blocks. So here's a 9 by 9 bi-clustered matrix. And the point is that we should be able to permute into latent blocks. Okay, so latent block structure will help us bound U max, and will also help us bound the quasi dimension. Okay, I like to have different definitions for the same thing, because in different times, different definitions help me visualize what's going on. Definition 2, that is equivalent to thinking about a KL matrix as having a latent state, i.e. our matrix with each row has some, if it's KL bi-clustered, each row can be in one of K latent states. So maybe this row is state 1, this is state 2, maybe this is state 1, maybe this is state 3, and so forth. And likewise, each column is in some latent state. So we have a latent state for each row and thing. And then we have some function or matrix that maps, if I'm in state K and that column is in state L, then my resulting label is this, and this is arbitrary. So it's given by some interaction function and a set of latent states. And that's definition 2. And finally 3, it's nice to think about this as a matrix. We can take a matrix and we can decompose it into 3 matrices. First matrix is this arbitrary interaction matrix. And then we have what we call block expansion matrices, where, you know, a row block expansion matrix basically just says, okay, here's a row in the thing. We add a new row that looks like that. Or here's a row here and we add a row that looks like that. Then a column expansion thing does the same thing except with columns. So yeah, so if we can blow it up with this thing. So these are the three ways I think about latent block structure. They're each kind of useful. Okay, more things about latent block structure. Okay, I'm quickly running out of time. Okay, so thinking about, you know, people often talk about matrix completion in terms of finding a good low rank clustering. So we say matrix has a rank D decomposition if there exists some matrix P and there's some matrix Q such that we can, yeah, it's rank D. This is the normal assumption behind it. It's specified D, M plus N. By clustering is the same thing as before. It's kind of interesting to compare by clustering to rank things. We kind of need less comparative parameters. We have some KL parameters and then some M plus N integers. And we call, if we have a KL by clustering, we'll say the complexity of it depends upon the minimum of K and L, okay? And so in terms of our basic bound depends upon, one term is this max norm squared. One can show that it's less than the rank, and one can show that its rank is then less than this bi clustering thing dimension. Is, so in summary, low rank assumption, you know, we have factors, our latent thing state is a vector in Rd. The matrix entry is created by the dot product. By clustering, our latent factors are integers, and then we get the matrix entry by some arbitrary function of the states. Okay, this is an aside. So I just want to point out, people normally think of bounds for matrix completion as depending on the rank, but when you do think about max norm thing, max norm can be much smaller than the rank. This is a little bit of an aside. I do it really fast, but basically you have a problem that looks like community detection, similarity prediction. Actually, I won't go through it, but basically the max norm is a constant, whereas for the number of communities you have, the rank is K. Okay. Okay, so this was our first term, our max norm, and we kind of showed how we could bound that. I'm already, okay, I'm going to speed up. So now we have site information in each row and column. The term in our bound that's going to depend upon the site information is going to be this quasi-dimension. If we have no side information, that's kind of like supplying identity matrices as our kernel, and you know, we call it quasi-dimension because then it just reduces to the dimensionality of our you know, the cardinality of our sets. Okay. Yes. Too much, but essentially we prove bounds on the side information, and the bound that we use for this paper for this result is the following. But depending on this sort of problem that you're working on for inductive matrix completion, these kind of guarantees are quite different. The high-level feature of the bounds, I know I'm going quite fast now, is that we have a term that looks like this in our side information bound. And this kind of, if we think about what this term is, this looks like a mistake bound for multi-class kernel perceptron, where the classes are the latent factors. What that means is this term will tend to be small if in some sense the similarity corresponds to the latent factors, i.e. it's somehow well predicted by the kernel. And then these are kind of technical properties, which I don't have time to go through. Okay, switching to multitask learning. Okay, so now we get to the game. Let me just look at my notes for a second. Okay, so to do things fast, okay, we said we're going to reduce the problem to inductive matrix completion. So what are the kernels we're going to use? Well, the row space is where we're going to get our inputs. So maybe we're asked to class, this is going to correspond to our stream of inputs. So this will correspond to the kernel supplied by the user. This dimension is going to correspond for time. And so we need some sort of kernel that basically kind of forces, this point tends to be more similar to that point than it will be to a point far away. So we need some sort of kernel for time along the top thing, kind of saying that things are sequentially related. Okay. This kernel for time, I won't go through the properties of, but essentially it's a path tree kernel. And essentially you can imagine that this is labeling the time axis, and it's labeling states. And so whenever a state changes, we pay a little bit. That's this KF. Then we also kind of pay additionally for the length of this chain. Okay, so this is our path tree kernel, and we have the kernel given to the user. And here's how the reduction works then. So here we can imagine this is kind of what our data sequence looks like. Here we're going to have 3 independent time streams. So in task 1, maybe we see 4 entries, and maybe task 2, we see 8 entries. In task 3, we see 4 entries. On our matrix, we get the inputs from the kernel. And so here, for each task, we kind of have its own separate time kernel joined together into one big kernel, kind of forcing sequentiality within each task separately. And the point is so say first one function was good, that corresponds to, say, some coloring of red. And so all these red rows or columns are exactly the same. These green things correspond to yet another function in our RKHS. And so this matrix itself, well, right now, let's pretend in this example, I haven't done it that way, but we could have 16 different data points. We could have just seen things straight along the diagonal. But the point is there's at most 1 observation per column, but we could see the same data point twice. And so we could have multiple observations per row, possibly. But what's my point? My point is, I think this is the reduction. Each of these in our max norm term, we kind of pay for the number of distinct colors, because this is our so each mode corresponds to one part of our our bi-clustering. Time corresponds to the other dimension. And this is the reduction. I kind of have to go through the maths a little bit more to give you more of a detail. I've quite overrun. Please accept my apologies. Just some open problems here. Algorithm runs in cubic time. We have this excess here. We do have a little bit lower bounds. We'd like to self-tune the parameters. In general, I plan to work more on memory. So we'd like to do this for things other than RKHSs, generalized loss functions. You know, the algorithm that we considered is switching, but I kind of in the back of my mind, I imagine each of these tasks are agents. And is there some sort of way to get similar bounds where these agents are communicating with less information? And I thank you for your time, and I apologize for much exceeding the time bound. Any questions?
No problem. So thank you very much for giving the talk. I'll stop the recording, and then if we have any questions.